Hey guys, welcome to Unit 5. I'm going to dive right into kinetics. And so this is, when we're talking about kinetics, we're talking about the rate at which reactions occur. So we've talked about chemical reactions and what types we have and things like that. But we need to talk about the rate at which they occur because it varies quite a lot from one chemical reaction to another. For example, look how long this reaction takes. That's pretty cool. We had to sit there for several seconds before anything interesting happened. So when we're talking about kinetics, we're talking about the rate of reactions. So when we're looking at our triangle here, we're really looking at the particle level. What's really happening? When these guys smash into each other, what's really going on? And so we have to have a theoretical explanation for what's going on at the particle level and try to explain that with a model that fits as closely as possible to the data we see. So again, we're trying to tie all these things together. What's our theoretical, what's our math, and how's that relate to what's really happening? And then how's it relate to what goes on in the lab? So we have this thing called collision theory, and it basically explains the way we think about atoms and molecules and compounds as they interact with each other. And so the idea is everything's always in motion, right? Unless you could get to absolute zero, you'd always be in some kind of motion. And as they move around, sometimes they bump into each other. And there are three possible things that I can think of that would occur when two compounds collide into each other, two particles collide with each other. So what I want you to do is pause the video, and you want to do this every time I ask you to do this. So, your learning is not something that you can sit and watch. Your learning is something you have to be doing. So when I tell you to pause the video and answer a question, it's even a good idea to, get in a call with somebody, share this video, watch the video together and stop and discuss the answer to the question too. So that way you're kind of engaging your brain and you're building your learning instead of just hoping that stuff sticks as it flows over you. So pause the video now and try to answer this question. Like I said, three things I can think of. So hopefully you came up with three possibilities. One, they could just bounce off of each other, like we've talked about with gases or whatever. They don't interact at all. Two, they could have intermolecular forces that allow them to be attracted to each other, either temporarily or for a longer period of time. And three, the collision could cause a reaction. If they collide in the correct orientation with the right amount of energy, you can get a chemical reaction. And that's what collision theory really talks about. It's about particles colliding so that they react. What they do is they form some kind of intermediate, some kind of temporary structure that then breaks in a different way, leaving compounds that were different than what we started with. And that's what happens with a chemical reaction. So we're looking at these different possibilities here of collisions. You can see ineffective collisions when they hit in the wrong alignment. So if the center oxygen is not the one that's going to be involved in the reaction, because we're going to leave some O2 here. So we're not going to do that by knocking off both the two outside ones or taking the middle one. We're going to knock off one of the ones from the end. So the reaction has to hit with a proper alignment. We can't just hit, oxygen to oxygen because those don't stick together. We can't hit, with the oxygen in the middle because that's not one that's going to be bonding to anything. So you can see that there's ineffective collisions here where they just bounce off each other and end up with the reactants again, right? So these are the same as the reactants were over here, and so are these. To get the reaction, the idea is they have to collide in such a way that it makes that resulting compounds, make those products favorable. This transition state, or sometimes we call it an activated complex, this is where those compounds come together. So, in this right here, there's a brief moment where all of these atoms are stuck together into one big molecule. And so that's the idea behind an activated complex, is that there's this temporary intermediate where they stick all together and then they fall apart in a new way. And so that's what we're seeing here with hydrogen gas, oxygen gas, and water being formed. So they make this activated complex. This is extremely unstable and only lasts for an instant, but then it falls apart. So it takes energy to get into this state, and then we get energy out when we come out of this state. So this idea is that chemical reactions occur because these compounds collide with the proper orientation. And they have to collide with enough energy. And this energy, maybe you remember, Pause the video and see if you remember what this energy is called. The energy required to make the reaction happen. So hopefully you remember that that's called activation energy. Activation energy, we call that EA. That's on your equation sheet in a couple of different equations, or in at least one. So I only see it in one, but that's an equation that happens in Unit 9, so not anything we need to worry about now. Activation energy, though, is that energy that has to be put in, that has to be available to make the reaction happen. It's the activation energy is what's required to form that activated complex where we're looking at back here. And that energy comes from the environment. It comes from the speed of the molecules. So like I said before, we're not just colliding with enough energy. We've also got to collide with the proper orientation. So a lot of the collisions are going to occur and not cause a reaction. Because of that, we can end up with reactions that are faster or slower because it's hard to end up in that orientation. So you can think about the speed of the reaction being based on, how often these collisions occur with the proper orientation and with enough energy to form that activated complex. Right? So those two things have to be true for that reaction to proceed. And the more often that happens, the faster the reaction will happen. The less often it happens, the we have a slower reaction. So some of this just depends on the nature of the reactants. Some are more reactive. Some compounds, some atoms are more likely to give up electrons or more likely to share electrons or form new bonds, things like that. Some things are just more stable than others. And we've talked about stability of ions, things like that in different compounds. The concentration, of course, matters because the more crowded they are, the more often they're going to collide with each other. And the more of those collisions are going to be in the appropriate orientation with enough energy. So, for example, I have a reaction that I'm about to show you that involves the combustion of sugar, of candy, basically, of some Smarties. And I think I did a Dum Dum too. I'll show you it once with just burning a Smartie with a Bunsen burner. And you can see that you can catch it on fire. So I've got a Smartie here. I'm going to try and burn it. You know it's got energy in it. First thing that seems to be happening is it's melting. It's getting hard to hold on to. But it is burning. You can see that it's got some flame on it. A little bit anyway. It's a lot like burning a marshmallow. It doesn't burn very quickly or aggressively. Ooh, it does stick to the table pretty good. Well, whoever's lab station this is, sorry about that. We can make it much faster and release a lot more energy at once if we can increase the concentration of oxygen available. And that's what I'm going to show you in this next video. The test tube has potassium chlorate, but I've made it molten. And what happens then is it releases a huge amount of oxygen gas. And so the oxygen gas is in that test tube. The test tube is warm, and I drop in the candies. And so that's your combustible material. So I've got some heat. It's a much lower amount of heat than would normally take to burn, to set fire to candies, to Smarties or Dum Dums, because I do both of those. But because there's so much oxygen, there's such a high concentration of that reactant, we can make that reaction happen very quickly and very easily with a lot of energy release. It's a pretty cool one. We call this one feeding the dragon. So here I'm melting potassium chlorate, which is going to release a whole bunch of oxygen gas. I'm going to shut the fire off so it'll still be plenty hot, but not really hot enough to ignite sugar, unless there's a excess of oxygen gas, which in this tube right now, that's what we're developing. This whole tube is filling with oxygen gas. And it's pretty warm, so when we add something combustible, it'll burn pretty well. So I got a bunch of oxygen gas in this tube now. Here comes the combustible. These are Smarties. Just torch some kid's desk. So I'm turning off the flame, and I'm going to drop the Dum Dum in there. The amount of surface area, especially when dealing with solids, is kind of a big deal too. We have to be able to, have these atoms aligned next to each other. And if you've got them all, locked into a big crystal, those middle ones are not going to get access to the other reactants until the outer ones are gone. But if you grind that up into a powder, you can get those things all at the same time. So you can make the reaction happen much more quickly. So we're doing a similar thing in this next video, only instead of candies, I just use granulated sugar. So a lot more surface area. And I've got the potassium chlorate there to provide the oxygen. And also in this one, we're going to use a catalyst, which is going to be in a couple of slides in the next slide here. So watch this. So this is the same demo that I just did in that test tube with the dum-dum. But this time I've got sugar and the potassium chlorate. So the oxygen is there, the sugar is there. But to release that oxygen and to get it going, I need a catalyst. So I'm going to use a catalyst in this. In addition to adding a catalyst, I'm also increasing the surface area. So that should make the reaction happen a lot faster too. So this should be interesting and a little bit frightening. So what you just saw was all the calories in less than a quarter cup of sugar right there. That's a lot of energy. That's a pretty good one. Smokes up the hood quite a bit, makes it pretty messy, and it's hard to clean up. Good reaction though, lots of fun. Of course, the temperature increases the reaction rate. If you increase the temperature, you're going to increase reaction rate for pretty much everything. And you should be able to think of 2 reasons why, right? Name 2 reasons that increasing the temperature increases the reaction rate. And we've really kind of already discussed this, but pause the video here, check with your neighbor or just, with yourself, or tell your dog about it, whatever. But try to come up with 2 reasons why increasing the temperature will make the reaction go faster. So 2 things. When they're going faster, they collide with a lot more energy. And so much more likely to have that activation energy, have that much energy in the collision so that the reaction will proceed to form that activated complex. The second one, of course, is when you're moving faster, you're going to collide more often. That's just the nature of it. Now, a catalyst can get a little bit more complicated. Essentially what it is, though, it's any compound that makes it so that a chemical reaction proceeds more quickly and it doesn't get used up. But at the end of the reaction, you have the catalyst still that you had at the beginning. You had the same amount and everything. So it's not actually used up in the reaction at all. It's just being there makes it go faster. So it speeds up a reaction and it doesn't get used up. This is a catalyst. Sometimes it forms an alternate intermediate with the reactants, meaning by being there, when we bring those things together to make that activated complex, that catalyst is sometimes involved in there. And it may even get changed. The catalyst may get changed in there, but it makes some complex that has a lower activation energy than the original one. This curve here, we need to be familiar with this kind of graph. This is really common. You'll see this a ton. I've got 2 different curves, the purple and the green. I've got 2 different peaks, both labeled C, and one of them has a height of B and one of them has a height of A, and those are both energy. So what we're looking at is, here's the energy that's in the reactants, right? So we think about energy, and we'll get to this quite a bit later, but you have energy in the system and you have energy in the surroundings. And so you can take energy from the surroundings and put it into the system, or you can take energy out of the system and put it into the surroundings. In this case, since we've got this energy in the reactants, there's a certain amount of energy there. We have less energy in the products. So the system is the molecules and atoms involved in the reaction. So all of the energy in the system is in the reactants here. All of the energy in the system is in the products here. So the amount of energy we had at the end is less than what we had to begin with. So it released energy into the environment. This is an exothermic reaction. It released energy out. And so we have this activation energy that we have to overcome. So this peak here, this is the activation energy of the original reaction. This is what using a catalyst does. So a catalyst, this is the catalyzed reaction. The amount of energy required for the catalyzed reaction is much less than the uncatalyzed reaction. You'll see a graph like this often, but you should be pretty comfortable with this graph. Sometimes we identify catalysts as homogeneous or heterogeneous. What we mean by this is simply what state is it in. If it's in the same state as the reactants, then it's homogeneous. If it's in a different state, then it's heterogeneous. Sometimes we have gases that react on a solid, and the solid is actually a catalyst. So that would be a heterogeneous, to give you an idea. Other times it'd be like all of it's in solution, including the catalyst. So that would be homogeneous. So they could work in a couple of different ways to speed up the reaction. Like I said, sometimes they are used up in one step and then reproduced again at a later step. And so you end up, you have it at the beginning, you have it at the end, so it's still a catalyst. It speeds up the reaction, it lowers the activation energy. That's a catalyst. But in the middle, it doesn't exist anymore. It got turned into something else, and then it comes back. So that's one way you can have a catalyst work. So sometimes it's just there, and its position makes it so the reactants are held together in a certain way that makes that reaction more likely. It lowers that activation energy by putting those molecules in the position to make the reaction happen. This is the way a lot of biological catalysts, enzymes, this is the way enzymes work. They a lot of times just grab the compounds and put them together, or they'll grab a compound and stress a bond so that it's much more likely to break, simply by the way they hold it. So on the left here is that graph again. On the right is a similar one, but this is one that we have to put energy into. We're getting out less energy than what we put in. When we go to measure the activation energy, we have to measure it from the reactants. That's our starting point. Doesn't matter where our starting point is, but from there, the activation energy is from our starting point to the highest peak. And so from our starting point to the highest peak. So you can see that the reaction on the right has a lot higher activation energy. It's much harder to make that happen. Delta H is kind of going to what we were talking about before, exothermic, endothermic. This is about energy coming into or out of this reaction. And again, we're talking about going into the system or coming out of the system. Energy going into the system is a positive value. Energy coming out of the system is a negative value released by the system. So you think about the energy in the system, final minus initial, that's your delta H. That's your change in the energy there. So you can look at this reaction, you can see each of these two reactions, you can see, I guess it's the same reaction going in opposite directions. Here's the energy we have in the reactants. Here's the energy we have in the products. So you should be able to pause this video and tell me the sign. Is it positive or negative for each of these reactions? And like I said, it should be pretty simple. Check with your neighbor if you got one, but at least pause the video and see what you can get. So if you think about delta H, it's the change of energy. We have less energy here than we had beginning. So if you have a small number minus a large number, this is going to be a negative delta H. And this one over here is going to be a positive delta H. And really, this is not something you need to worry about too much right now. This is going to come up later on down the line, but it's good to start thinking about this because it's just something that runs through a lot of chemistry. So endothermic, exothermic, this one is exothermic. Exothermic reactions release energy to their surroundings from the system to the surroundings, right? They have a negative delta H. Endothermic reactions, energy has to be put into them. They take energy from their surroundings. So energy goes from the surroundings to the system. I think that's pretty straightforward, and it'll come up again later, like I said. So that ends today's lecture. Hopefully you guys are able to make sense of all that. We'll start getting into the math of this in the next lecture. When we look at our triangle here, we're really looking at this particle level. Oh no, now we're looking at the lab. Oh no.